You know, it's funny, a lot of life's puzzles, from really simple choices to way more complex problems, are basically just math problems waiting for us to solve them. Today, we're going to grab our algebraic toolkit and do exactly that. And we're starting with a classic race.
All right, let's kick things off with a great little scenario. Picture this. You're in a race against a horse. Now, you get a head start, but you're a bit slower. The horse is way faster, but it has to get saddled up first. So who wins? This isn't just some brain teaser. It's a math problem in disguise, and we're about to crack it wide open.
This whole race scenario, it's a perfect real-world example of what mathematicians call a system of linear equations.
So what in the world is that? Well, don't let the fancy name fool you. It just means we have two or more straight-line equations that we're looking at together. The solution is just the one single point where those lines cross. It's the spot where both stories, or both equations, are true at the exact same time. It's where they agree.
We can actually translate our race into the language of math pretty easily. For you, the distance you travel, we'll call it d, is just your speed 0.2 multiplied by the time, t. Easy enough. For the horse, its distance is its speed, 0.5, times its time. But its time is t minus 6 because of that 6-minute delay. And boom, just like that, we have our system.
Now, if you graph these two equations, the solution just jumps right out at you. Your line starts at the beginning, at 0, and goes up steadily. The horse's line, though, starts later, over at the 6-minute mark, but it's way steeper. And that spot right where they cross, that's our answer. The horse catches you exactly 10 minutes into the race after you've both gone 2 kilometers.
Okay, but let's be real. Graphing is great when the answer is a nice clean number like 10. But what if the answer was 10.37 minutes? Or what if the numbers were huge? Trying to draw a perfect graph every time can get really messy, and it's not always precise. We need better, more reliable tools.
And that, my friends, brings us to our algebraic toolkit. These are 2 rock-solid methods that will give you the exact answer every single time, no matter how messy the numbers are. Let's talk about substitution and elimination.
First up is the substitution method. The whole strategy here is pretty clever. You just solve one of the equations for one variable, get it by itself. Then you take that whole expression and plug it into, or substitute it into, the other equation. Suddenly, you've only got one variable to worry about. Solve for that, and then plug that answer back in to find the second one. Done.
Our second power tool is the elimination method. And you can think of this one like a perfectly balanced scale. The whole goal is to add or subtract the two equations together in just the right way to make one of the variables completely cancel out, get eliminated. That leaves you with a super simple problem to solve.
So how does it work? Well, it's pretty methodical. You line up the equations. Sometimes you might have to multiply one of them so that the coefficients for one variable are opposites, like a positive 3x and a negative 3x. Then you just add the two equations together. And poof, one variable vanishes. Solve for the one that's left, and then, just like before, plug it back in to find the other.
Now, these methods are awesome, but like any powerful tool, you got to use them right. So let's talk about a couple of the most common traps people fall into, just so you can sidestep them completely. Here's a huge pro tip for you. Stop automatically trying to solve for y first. I don't know why, but we're often taught to do that, and it can create a ton of extra work with fractions and negatives. Look at the equations. If there's an x all by itself with no number in front, solve for that first. Always, always look for the easiest path. It's faster, and you'll make way fewer mistakes.
And oh man, here's the other big one. You do all this work, you find that x equals 2, and you think, yes, I'm done. But you're not. Remember, the solution to a system isn't a number, it's a point on a graph. It has an x value and a y value. Finding that first variable is only half the job. You have to take that answer and go back to find its partner.
So far, we've only dealt with systems that have one perfect solution, one point where the lines cross. But what happens when you're solving a system and something weird happens? What if you do all the math correctly and your variables just completely disappear? Let's figure out what those strange results actually mean.
It turns out there are 2 special cases. If you do all your algebra and end up with a statement that's just plain false, like 0 equals 1, what does that mean? It means your system is inconsistent. Visually, the lines are parallel. They never ever cross, so there's no solution. But if you end up with a statement that's always true, like 0 equals 0, that's a dependent system. It's a sign that your 2 equations were really just the same line in disguise. They overlap everywhere, which means there are infinite solutions.
Okay, So we can solve for x and y, and we can figure out when a horse is going to catch up to us in a race. That's cool, but why does this fundamental skill actually matter in the big picture?
Because, and this is the key takeaway, these ideas of substitution and elimination go way beyond straight lines. They are the absolute fundamental building blocks you need to solve incredibly complex, non-linear systems. You know, the kind that actually model the real world's messy curves and complicated shapes.
And that brings us to the real impact. These skills are absolutely essential in pretty much every technical field you can imagine. Engineers are using them to design circuits. Economists use them to model markets. Physicists use them constantly. And computer scientists use these principles to build programs like MATLAB that can solve unbelievably complex problems. Mastering these basics really does open up a whole world of possibilities.
So, think about it. We started with a simple race and ended up talking about the foundational math behind modern science and engineering. And it all began with just figuring out where two simple lines meet. So that leaves us with one final thought. If we can model and solve simple choices in races with lines, what other, much more complex parts of our world are just out there, waiting to be understood with the right set of equations?